Okay, we're gonna finish up journal bearings today. We've got to figure out how to use all those charts in the book in chapter 12. This is chapter 12 of Shigley, and last time we talked about Petrov's equation and why it wasn't quite something that you would use in an analysis of bearings for one very large reason. We're going to look at what you can do. Now, what you can do is governed by Reynolds Equation. The problem with that is that it is complicated. In fact, let me show you what it looks like. Let's see this. That's a blank screen. Put this in here. Whoops, not that. There's Reynolds Equation. This is just out of your book on page 621. So this would be Reynolds Equation with side flow. So side flow means the oil leaks out the sides. You know, there's no caps on the end of the bushing or anything. So some oil lubricant leaks out those sides. So this equation accounts for that. The problem with that is there's no analytical solution for this equation. So you have to do some tricky math and a lot of different things to figure out some analogies. They even mention electrical like circuit analogies on how to produce a solution to this, or at least an approximation to it. And so that's been done and encapsulated in charts, lots of charts. We looked at one of those charts last time. So that's what we're going to do this time. Let's look real quick though at back over here so we remember all of our terms. So let's just draw a bushing, maybe here. So this is the bushing. You know, it's mounted in some housing or bracket or whatever, and it's stationary. And inside there you've got the journal. The journal, I'm going to draw a little bit smaller one. Remember, it doesn't sit center concentrically with that bushing, or it might sit there for a little while, but when it's in operation, it's going to move some. I'm going to exaggerate it. Normally you have super tiny clearances, but just so we can see things, I'm going to exaggerate it. So maybe our journal is over here, and it doesn't just drop straight down either. When it's spinning, the fact that it's spinning will pull it to one side, so it'll be something like this. So it's sitting over here. In fact, your book has a diagram similar to this in it. In fact, let's see if I can find that. Here it is. Well, part of this. Now they've got a couple of other things, so you can kind of see there's a H0 for us. That would be kind of right here. That's your minimum film thickness. So it's talking about the lubricant being the film, and that's the location where it is thinnest. So minimum film thickness. On this other diagram, you can kind of see a pressure distribution. Remember what we did when we calculated pressure last time was we just used a projected area, kind of like you would with a bearing stress in between a bolt and a hole that the bolt is in. But this is more realistic pressure distribution. Also notice that the minimum film thickness is not exactly where the maximum pressures. The maximum pressure's over here a little bit. So they're not exactly at the same point. Just because that's the minimum film thickness does not make that the maximum pressure in the fluid. Let's see what else is labeled on here. Well, this angle. So this angle can be discovered from one of these charts, and it talks about how far from this vertical axis is your location of your minimum film thickness, and then there's a similar angle for the location of your maximum pressure. There's this angle. I think this one might be in your charts. I don't actually remember where this one is right now. It just shows where that pressure kind of decreases, where the pressure supporting the weight and the radial force in that shaft, where it decreases at or goes to zero. Here you can also see the angle of rotation. So this shaft would be spinning clockwise. So and it's actually shifted over to the left a little bit. So here, this O prime, that would be where the center of a concentric journal would be if the journal was concentric in the bushing. This is its original location, and you can see it's dropped down and to the left a little bit when it's spinning clockwise. If it spins counterclockwise, then it would drop down and to the right. So that's where a lot of the terms, oh, I see another one, E. So this is the eccentricity. So basically how far off of the original center is the journal's center after all of this movement has occurred. So there's a little distance there of how far it's moved, basically. All right, so I'm going to use Mathcad to, now you got to be careful here because a lot of this information comes from charts, which means that you can't program it in Mathcad unless you go and program the chart, I guess. But you can't just go in and program all of that into one sheet that's going to automatically update, because you have to do a lot of reading from charts. But there's a couple of things we can program in, and so let's do that. We're going to create a situation where we're going to design the clearance between a journal of known diameter and speed and everything, and the bushing that we don't actually know. And so the journal diameter is going to be 2 inches. So we just plug in lowercase d for 2 inches. Most of the stuff that we need from the charts are going to reference the radius of this. So I'm just going to go ahead and say the radius is diameter divided by 2. Now, I am going to use inches. I believe all of the charts of this type in your book, actually, well, there are a couple of charts that have, I guess you might call them metric viscosities and things like that, but a lot of this other stuff is going to be dimensionless. So Sommerfeld number is, basic bearing characteristic is dimensionless, so it actually doesn't matter as long as the units you're using work with one another. We're going to spin this shaft at 500 RPM, and Mathcad's going to take care of all of my units that I'm needing for converting if I have minutes where I need seconds or something like that. L. So L is the length of the overlap between the bushing and the journal. A lot of times this is the length of the bushing, because normally the bushing is a little shorter than the length of the journal. Sometimes they're exactly the same, but rarely are they exactly the same. But it's the overlap between the journal and the bushing. So I set this at 1/2 inch, so not very deep. It's pretty shallow bushing. Let's see what else we have. We need, for a lot of these charts, we need a ratio of L over D. We just need to know what that ratio is. So for us, that's 1/4. No units on that. It's just 0.25 or 1/4. In the charts, it's going to be shown as 1/4. We're going to have this shaft supporting 200 pounds. And I think that is all of the information. Let's move some of it over here just to save us some room. That's all the information about the shaft and its operating characteristics that we need to get started. And the big thing that we don't have here is the clearance. C. We don't know how much space is between the journal and the bushing that it's in. So that's what we're going to work to find. One of the very first things that, actually there's one other piece of information. We need to know what type of lubricant we're dealing with. So let's use SAE, and I used 20 at 150 degrees Fahrenheit. So these lubricants, these oils, whatever it happens to be, they change viscosity with temperature, and so I need to know what temperature I'm running this fluid at. There's not a super easy way to get this 150 number because you have to know a lot about the machine that's running this. So a lot of times this is more, I want it to run at 150, and I'm going to do whatever cooling it takes to keep the lubricant at that temperature. So I'm going to have water jackets that cool it, or I'm going to have a circulation system where it exits this part of the machine for a while and cools down. It flows, it's a whole circulatory system type thing. So this 150 number is more difficult to calculate. It's not impossible, because in a little while at the very end of this, we're going to calculate the power lost in the fact of how we've set up this journal. And that power loss goes into heating the lubricant. So you can figure it out. In this case, it's more of kind of like a design constraint. I want it to operate at 150, and I'm going to do things outside of here, wherever I'm at with the journal and bushing, that are going to keep the lubricant at 150 degrees Fahrenheit. If it changes from that, particularly if it gets hotter, then my viscosity is going to drop. So how I deal with this is I go to a chart, and this chart in particular, this one, there's 3 of these, I believe, in your book for different types of lubricants. So here's the SAE, and there's 20. That's the one we're using. And down on the x-axis, I have 150 degrees Fahrenheit. This is figure 1212 in your book. And all you do is you just read off the chart. So I'm going to try to draw here. So basically, there's the 150 line. Let's draw in a different color. Right there. And then I just need to read basically that number. So it looks like for us, the viscosity, now the units here are in, I don't know if you can see them, but they're micro Ren, R-E-Y-N, that's Ren as in Reynolds number. And so that's micro Ren. And it looks like we're at 2.4 micro Ren. Now, Mathcad doesn't know micro Ren, so I'm going to have to tell it what that means. So let's get Mathcad back up. And I'm going to tell it, I'm going to define that a Ren, I think at least my version of Mathcad uses poise as the units for viscosity. And I don't want those, I want Ren. And so a Ren is a PSI per revolution per second. And Mathcad does know all of those units, so I can just define a new unit for Ren here. And then I used our viscosity from the chart that we just looked at was 2.4 times 10 to the negative 6th Ren. All right, so now we've got Ren as a unit in our Mathcad sheet. And you can do that with any kind of units that you might need to create. As long as you can break them down into units that Mathcad does know about, then you can define a new unit. All right, so we have our viscosity. Let's see. We need to calculate our Sommerfeld number. Well, actually, we're not going to calculate it because our Sommerfeld number needs C in it. So the clearance, C, it needs that, and we don't have that yet. That's actually where we need to start. So let's look at this chart. Oh, there it was. And this is figure 1216. Down here we've got the bearing characteristic number, the Sommerfeld number, and we know most of this stuff. We know R, we know that's the radius of the journal. We know the speed it's running at. We don't know P, but we could calculate that real quick if we wanted to because we have all the information to calculate that. In fact, we probably should do that pretty soon. We just found our viscosity, but we don't know C. We don't know the clearance. That's kind of where we're starting on our design here part, is designing how big this bushing needs to be. So what we're going to do is we've got these 4 traces on here. These are the L over D. So we calculated in our Mathcad sheet that L over D was 0.25. So that's this 1/4 line. So this line, this trace down here, governs our situation. There's these 2 dotted lines, max W. So where this max W line intersects our trace, that is where the clearance, or where this set of bearing characteristic and film thickness would support the maximum weight W. Not necessarily weight, but the maximum force. We called it W, pushing straight down. There's this other one over here with this dotted line, and where it intersects way over here somewhere, that's going to be the situation that creates the minimum friction in in the fluid between the journal and bushing. What we want to do is we want to figure out a clearance that creates a situation kind of in between those, so somewhere in the middle. So how we're going to do that is we're going to get the Sommerfeld number from here, off the chart there. We'll do a better job. These charts are kind of small in your book, so we're just going to have to stick with kind of, some approximations here. And then over here, it looks like it intersects maybe right there. So we're going to get this Sommerfeld number, read it off the x-axis, and this one. And then back out the value for C for both of those scenarios. So let's go to Mathcad and do that. All right, so first, we do need to calculate pressure. Pressure is just W over the diameter of the journal. So 2R, we have D plugged in, times the length of the overlap between the journal and the bushing. So here's our pressure. We'll put it in PSI, 200 PSI. So we've got that. And this is not the maximum pressure. This is the same one that we calculated last time when we were doing Petrov's equation. All right, for our first scenario, let's turn off Mathcad. Let's get this number that looks like it's around 0.45 off of the x-axis, the one that relates to the maximum W, maximum weight supported. So let's get that Sommerfeld number going. Remember Sommerfeld, S equals, and so this is the bearing characteristic number, Sommerfeld number at the x-axis on all of these charts. They give you the equation for it, and it is S equals R over C squared times our viscosity times N, speed, over P. When you solve this, you should come out with a unitless, dimensionless parameter. And so you do want to make sure that when you're doing this by hand, you've got all your units working to cancel each other out. What we want to do is we want to solve this for C, though. So it gives us this. Actually, there's two. We don't want the negative one. We just want the positive one. So let's get that and say that C equals that thing. And for our first case, we're going to say that S, the Sommerfeld number that we read off the x-axis for the intersection between the maximum load dotted line and our 0.25 L over D trace, is 0.45. So this 45 just came off of the reading the chart. In fact, let's make sure that we're good with that. So that is reading, right down here somewhere. And so you have to do some little approximation and count the number of spaces between everything. And we're going to count that as 0.45. All right. Oop, we need Mathcad. All right. And so now we can solve for C. And we want it in inches just to see what it is. So it's really tall. It's tiny clearance. Half a 10,000ths, it looks like. We're going to do the same exact thing again. In fact, I'm going to copy and paste. But we're going to put in a new number for Sommerfeld. We're going to put in the one over here. So this is the other intersection point. This one, when I looked at it, I used, let's look at my number. I used 008 is what I grabbed off of the x-axis here. So let's go in here, put 008. And we get a little bit larger clearance needed to produce that. So here, there's a really tight clearance. This is maximizing the weight supported, so it's really compressing the fluid. Here, it's minimizing the friction, so there's more gap, so the fluid can flow easier. So I have two C values here. In fact, let's give them different. Let's do C1 and C2 so that they're different numbers. And our C that we're going to use in our design, so this is the design part, is just going to be the average of C1 and C2. So this is the clearance we're going to use, 2 thousandths of an inch. pretty much. There's a 003 in there, but we'll just use 2/1000 of an inch. Actually, Mathcad will use all of this. If we were talking about it, we would say it 2/1000. All right. Now, once we know that, we can actually figure out the size for our bushing. So the bushing diameter, we'll call that uppercase D, is just going to equal the journal diameter plus 2 of these clearances, 1 on each side. So there is the size. Oh, hold on. We multiplied. There we go. There is the size of our bushing. So it's a 2-inch. Remember, that was the diameter of the journal. So 2-inch plus 2 clearances. And this is, you know, reasonable. These are pretty tight clearances. You probably generally have slightly larger clearances, but this is in the reasonable range anyway. It is tight though. And so that's another thing you have to think about when you're designing something that's going to use these journals. Whatever journal, you know, if there's a whole series of these journals, they've got to be super well aligned in order for this to even work. Otherwise, they're going to crash into one another somewhere. In one, they're cleared, and in another, they're a little bit off, and there's contact. And so you've got to be very precise in your fabrication processes when you're using such tight tolerances. Okay. Now that we have that, we can start using our charts. One of the first things we're going to do is we're going to find the minimum film thickness. So this clearance that we just calculated, that's assuming that the journal is concentric in the bushing. We know it's not actually that way. So we're going to go and look at minimum film thickness. Actually, that's the chart we're already on. Minimum film thickness is the y-axis. We just haven't used it yet. So we are going to go find our Sommerfeld number for our clearance that we actually do have. So we need to grab, we can use this one. Plug that guy in, except we need it to actually evaluate. So let's, oops, change that to there. And here is our Sommerfeld number, 025. So what we'll do is we will go to 025. So there's 02, there's 04, so there's 03, 02 is right in there somewhere. And we'll read that number, this number right here. Now this is not the minimum film thickness on the y-axis. It is the minimum film thickness variable, and it's called H0. That is the minimum film thickness over C, which is our clearance. So it's actually the ratio of minimum film thickness to clearance. So we, from our chart, saw that 0.005, that's reading the y-axis off of this chart that we have down here where it intersects 0.05. Well, wait, we might have an extra 0 in there because this is 0.1. So looks like it intersects maybe right at this one. So this should be 0.0. Yeah, it's a little, it's hard to read. Maybe if we zoomed in, I'm going to round it up just because I can't resolve it very well. This one is 0.4, this one is 0.6. So this one in between is going to be 0.5, but I think I just typed an extra 0 in there. Yeah, 0.5. Which is going to make all of my stuff from now on, because I see on my other chart where it did this before that I had a 0.05 in there. All right, so 0.5. We'll get all new numbers. That equals, well, let's do control equals H0. So that is the minimum film thickness, but it equals this over C. So we actually have to solve for H0, which is not complicated, but I want to use Mathcad to do it anyway. So this guy is H0. And it equals 1/1000 or 1/10,000. So pretty thin. We're getting really kind of thin there on our clearances, but that's what we have. Oh, you know, I fixed it on my chart, so my other stuff is not wrong. I just typed it in wrong up here for some reason, but I fixed it later. All right. Related to this is the eccentricity. Remember that is, oh, you can't see my number. there's the minimum film thickness. All I did was I took H naught over C, that's the y-axis from the chart we were just looking at. Here is what we read off of the chart, 0.5, and then I just solved for H naught. And so let's go back to here. That's this location right here, or it's not the location, it's the distance between the journal and the bushing right there. Related to that is this eccentricity number. In fact, they're on the same chart. If you look at the other side, the other y-axis, eccentricity ratio is, I'm going to use E, I think it's actually an epsilon, but that is basically the ratio of how far off center it's moved. So if you're up here at 0, then it's still concentric, so it's right in the center. If you're at 1 down here, then you are actually contacting the bushing. And then this is basically a percent in between those two extremes. We're at the really close to contacting range, so we could just read this off of the chart and get 0.95, or there is an equation which basically is the same thing. Let's see, what did I even write down? I'm going to use, I guess we can use epsilon. Epsilon, I think it's in your book. Let me see if I can determine if it's E or epsilon real quick. Let's see. It's an epsilon. All right. And this is, it's not a numbered equation. It's just on page 630 in the middle of the book. So it is 1 minus H naught over C. So it's really just the other side of your clearance. So this is 0.95, the same number that we would read on the chart. So 0.95, or you can just go to the chart and read 0.95 over here. All right, whichever we want to do. All right, so this one, H naught, that is the minimum film thickness. So that's will give you the amount of clearance, basically in the smallest amount of clearance when this thing is running. Remember, we set up some speeds, 500 RPM. It's got to support 200 pounds. So we set up our dimensions. So under those scenarios, or scenario parameters, then this would be your minimum film thickness. Okay. You could also, there are charts for finding the location of this film thickness. They work very similar. In fact, let's see if we can. There's the position of minimum film thickness, so it gives you an angle to measure over from the y-axis, basically, to figure out where your minimum film thickness is. We're going to skip that one. It works the exact same way. You look up your bearing characteristic number, and you read it off the chart on the right trace, and you find that angle. We're going to go to film pressure. Let's see, where's film pressure? Flow variable, flow ratio, maximum film pressure ratio. We're going to do that one. Okay, so this is the ratio of the maximum pressure to the pressure that we calculated. We calculated early on, where do we do? P, right here. P is force over that projected area, but we know that's not right. That was if, you know, everything was just kind of sitting there centered up perfectly, but it's not. And so we need to find the maximum film pressure. Let's see, that was on page 23. So the one that corresponds to, well, this location where P max is right here, so right in there. All right, so there's a chart for that. This one, this is figure 1221. Again, it uses a Sommerfeld number, so we got to go remember what our Sommerfeld number is. Ours is 0.025 for our Sommerfeld number. So 0.025 is going to be, there's O2, there's O4, O3 is in the middle of that, O25 is in the middle of that, so we're right here. Draw a straight line when you try to do it. This one looks like it lands right here. So there's 0.1, 0.12, 0.14. So it looks like we're at 0.14 for our maximum film pressure ratio, P over P max. So let's write down, let's get this out of the way. 0.14 equals P over P max, and we will solve for P max. And then this thing equals P max. Let's put it in PSI. So 1400 PSI, remember the pressure we calculated was 200 PSI if everything was centered up and working somehow. It can't actually work when it's centered. You actually need, let's look at this. You actually need a small pressure and a large pressure over here. If it's all centered, then there's it just kind of equals out, and there's no way to support the weight. It would just sink to the bottom. So you actually need the small gap and the large gap to create the pressure to support the weight that you're trying to support. We're over here. So we're at 0.14, and actually we solved that one already. 1400 psi for Pmax. We could find there's one of these charts, I believe, that gives us the location of that Pmax also. Again, we don't really need that. What I want to do instead is I want to figure out, now that we have the pressure, the maximum pressure, the minimum film thickness, I want to find the power loss in this thing. So how much power are we losing? We didn't actually calculate how much power we're putting in, but I guess you could. You have a speed and, well, we don't have a torque really, but we can figure out how much power we are losing. And how we're going to do that goes back to similar to how we did a couple of the derivations in Petrov's equation, where we used that tangential force. And we're going to find the power loss by figuring out the friction. So remember, if we had, let me write some stuff. Actually, we might write some stuff down on paper. Let's go. All right, go here. So we do know that this is, there is a torque causing this to turn, and there's a friction in this fluid that's opposing that a little bit. It may not be a lot, but there is a little bit of opposition to that turning, because we know that we couldn't just set this thing to turning and then it would turn indefinitely. Eventually, it would stop turning if we stopped putting power into it. And so we know there's a frictional force, like a little tangential force that is acting on this journal to slow it down. And last time we said that in general, friction can be defined as this tangential force divided by a normal force. So if we use one of our charts over here, now there's not a chart that's going to directly give us this. We have to be a little bit tricky. Not tricky. We just have to be creative in how we use this chart. Let's see. That's the position of the maximum pressure, flow ratio, flow variable, coefficient of friction variable. This is what we need. All right, so this one, coefficient of friction variable, says the y-axis is measured as r over c, which we know both of those, the radius of the journal and the clearance, times f. So we can get our coefficient of friction from this chart. And then we can go back to this idea. We know F, we know our normal force was I think we put 200 pounds at the beginning, W was 200 pounds, and so we can calculate that tangential force. And that tangential force times the radius will give us the torque that's being applied to slow down the journal, and that will relate to the power we're losing. So first let's go find F from here. So we're on, actually this time we're on the top trace. L over D at 1/4 is the top trace. We need 0.025, which is, right here, right in there. And we're going to read somewhere over here. So it looks like 1.6 maybe. Let's see what number I actually used in my, where did I put it? I used 1.5, so I guess if you get really close in there, I'm using a really big marker on this thing. So 1.5 for our coefficient of friction variable, R over C times F. So let's go to Mathcad. So R over C times F equals 1.5, and we're going to solve for F. So there's our coefficient of friction variable, or that is the coefficient of friction. Now, taking that idea over to here, now we know this value is 3 times 10 to the negative third. Normal force is 200 pounds, and we can back out what our tangential force would need to be. Okay, let's do that in Mathcad. All right, I'm looking here. Let's see. Calculated F. We need to know the equation that I just wrote down. I'm going to solve it for F tangential. So F, we'll call that tang, would equal coefficient of friction F. So no, I don't want to do. I want to just use that F. Times our normal force. In our case, our normal force was way at the top, right here, the 200 pounds. So just times W. So this will calculate the tangential force. And let's put it in pounds. 0.6 pounds. Okay. Now the torque associated with that, so the torque that this guy's creating, it's creating this T from friction. That T from friction would be this tangential force times the radius. Okay, so I can easily do that, and we call it T from the tangential force is equal to F tangential times R, which is already coded in Mathcad. Let's put it in inch pounds. 0.6 because the radius is 1 for our shaft. Remember, the diameter is 2, so radius is 1, so that's why they came out the same number. And then power is torque times speed. So normally it's torque times angular velocity. Mathcad I can just put the speed in there and it'll work the units out for me. Except those units are really weird. Let's do horsepower. Why did I get some oddball units? Oh, because T, it's T tang. There we go. Not many horsepower are being lost. 0.005 horsepower. Actually, it's probably more like 477 horsepower. All right. So not a lot of horsepower loss on our setup here. But we have super tight clearances, so we do have to worry about heating up the fluid and all that kind of stuff with these tight tolerances. But that would be a way to calculate horsepower loss, or you can put it in any other kind of power loss, watts if you wanted to, but in Mathcad anyway. But you do have to remember that what we can't do in Mathcad anyway is, and in most of these things, because you're not going to have the charts coded in, we can't just go say, well, what if the speed was 1,000 RPM, plug in 1,000 here, and then expect everything to change, because we read so many numbers off of charts that wouldn't update live. So you got to be careful that you don't accidentally do that. All right, let's do a couple more, maybe 2 more things here, and then I think we will have the bigger ideas of how you go analyzing one of these bearings. These charts all work in a similar way, so if you want to use some of the charts we don't look at, they work exactly the same way as these charts. But let's do the flow rate and the side flow rate. So the flow rate is another one of the charts. Let's find it. Let's see. There it is. Flow variable Q over RCNL. So Q, this flow rate is the flow of the fluid around the journal. So it's the fluid flow around the journal. Now you might be thinking it's different rates, but this is going to be a volumetric flow rate, and what we will have, or look at one of the, here we go, is over here, you know, the speed of the linear velocity of the fluid is faster than it would be over in this more open area over here, but there's a smaller amount of fluid being able to push through here. Over here, the opposite is true. So the linear velocity of a particle of fluid is slower over here, but there's many more particles able to pass through this area. So overall, the volumetric flow rate around the journal is about the same, whether you're over here or any other place, because you have a changing volume that's flowing and a changing speed of how fast that thing's moving. So the volumetric flow rate is consistent pretty much around the thing. And that's what this chart, wherever it went, this one, is going to tell us. Now, again, we're on the very top line up here. So L over D is a quarter. Our Sommerfeld number has not changed. So it's still right in here, which is, you know, right in here somewhere. So we're going to be just over 6 for our Q over RCNL. I actually picked 6.2, which is where I marked it there. All right, let's look at Mathcad to put that in. So what we're reading off the chart is Q over R times C times N times L. All of that equals 6.2. And we're going to solve for Q. So there's Q. And it's in meters cubed per second. Let's put it in inches cubed per second. 0.3 cubic inches per second. So not too bad, not too much. Although this is a cubic inch of fluid per second. So it's still not slow, or I don't know if you count it as slow, but there's a lot of fluid flowing through around this journal. Now, the other thing we want to do is similar to this, but this is called the side flow rate. So this one, it's harder to determine just from the chart that, or where to go? This chart is the side flow rate, but it's called flow ratio. And QS, that's the side flow. What side flow is yes, there's fluid going around the journal, but there's nothing keeping the fluid from leaking out the sides, you know, either side of the bushing. And that's what this ratio is going to tell us. And we can already see that most of the fluid that we're going to have around the journal is going to leak out, and we're going to have to replenish it. So we've got to have a good pump system that gets new fluid in there constantly, because here's our trace, and this is a percent over here. So basically this is the percentage of fluid that's leaking out. Our bearing characteristic number, Sommerfeld number, is way up here. So, you know, 98% or so of our fluid is leaking out of the sides of the you know, the open sides between the journal and the bushing. So we're going to have to replenish our fluid pretty quickly. It's flowing around at that 0.3 cubic inches per second, and it's leaking out almost the same rate. So we've got to pump a lot of fluid into this one to keep it from going dry, and then there being contact, and we're just crashing our journal into our bushing. So I did read a 0.98 off of here. And so if we want to find the number, then the side flow rate is just equal to whatever number we read, 0.98% of the flow rate. So, and again, let's put it in inches cubed per second. So almost all of the fluid that is going around the thing is leaking out just about as fast as we can spin it around there. So we do have to make sure that we're replenishing the supply of lubricant. I think those are the only ones that I want to explicitly go through. There are, here's the number 0.319, and there's where I just did 98% of Q, where Q is the flow rate. So most all of it's leaking out. There's more, we didn't actually calculate the volume of fluid around our journal. You could do that with just a a volume of a torus type thing, or a cylinder, I guess. Not a torus, a cylinder, and to figure out how much fluid is actually around it. But so we may have had some really tight clearances here. Remember, our clearance was 0.02 of an inch when we found it out. Maybe you would want a little more, but again, you can't just go and change one of these variables up here to try and modify things and have your whole sheet, Excel, Mathcad, whatever it is, update, because so many things rely on reading a number off of one of these charts. So unless you have all these charts, set up as some kind of data set, then, or you've curve fit them all or whatever, then a sheet like this isn't going to automatically update. So just be careful that you don't assume it does. Okay, I think that is all we need to do for journals. There are a couple of other topics in your book on journals. I think they have to do, let's just look at them real quick. We didn't do the pressure angles. We didn't do where the film pressure ends at. There is a temperature rise equation, or not equation, a temperature rise chart. It is, if you want to figure out how much heat is being generated in the fluid itself. It does talk about the idea of pressure fed bearings. So you might force lubricant into one of these bearings versus them just being submerged in lubricant, or having a different splash system for how the lubricant gets into the journal and the bushing in the first place. Talks about a couple of materials, and then a couple more examples. But what we're going to focus on, I think we've covered all that we need to focus on. And next time, we're going to start with some gears, and look at how your book handles gears. And we'll do maybe 2 or 3 talks about the AGMA process for determining gears. All right, that's enough for today. We will see you next time.